Hello, my name is Aaron. I am a fourth year electrical engineering student at the University of British Columbia's Okanagan campus. This video lesson is the fourth and final assignment in the ENGR 459 Advanced Electromagnetism course, instructed by Dr. Kenneth Chow. Today's topic covers the wave equation and plane wave solutions as described by Maxwell's equations. So first, the wave equation. To describe a wave, I'll first just use a definition. That being, a wave is a spatial disturbance that moves at some velocity. This can be shown visually on a graph here. It's just some function f for a wave moving along a spatial domain such as z. You can consider two wave crests. The first at time is equal to 0. The second being at some time t. The distance traveled by this wave is just described by its velocity multiplied by the time. So the wave equation itself can be written as such. A spatial disturbance result in this temporal disturbance. This is the most functional form for the wave equation, and it can be used to represent sound waves, light waves, and water waves. Okay, so let us now move on to the also familiar sinusoidal form of a wave. Express our function just in the z direction over time as such. That's just equal to omega. Simplify this. Sinusoidal form of the function to look like this. So what we have is just our amplitude up front here. This is our spatial term of the wave. This is our temporal term of the wave. And this here is our phase shift. So this is the most common real form of a sinusoidal wave. Next, we'll extend this into complex form for a wave. And to get there, we'll just be using Euler's identity. Which can be written as such. So this function for a wave can then be written as the real part of our resulting complex wave. What all this looks like is now taking this theta term. And just the same theta there, of course. It can now be written as complex exponential as such. We can tidy this up a little bit. Performing the following operation here. And this just takes out our phase shift, separates it there. So finally, our complex expression for wave can be written as written with a complex amplitude and our exponential term with our spatial and temporal dependencies there. This complex amplitude is just the amplitude combined with our phase term from before here. So the advantage of working with waves in their complex form is that they're much easier to perform mathematical operations on.
All right, so moving on. These are Maxwell's 4 equations, and we want to see just how we can manipulate them to bring them into a form that looks like a functional wave equation. So to do this, we're going to consider a simple medium, like our electromagnetic waves are just going to be propagating through a simple medium, and all this means is our charge density goes to 0, our currents go to 0, and our relative permittivity and permeability here are both just equal to 1. So with these simplifications in mind, we can rewrite our Gauss's law just to be equal to 0. This just remains the same. Faraday's law also remains unchanged, and Ampere's law can be simplified to this form here. So to get our wave equations, we're just going to first look at Faraday's law here, and to get it to look like a wave equation, we apply the curl to both sides of this equation. So that'll just look like this. Now, from here, on the left-hand side, we can use just a vector identity for the curl of a curl. Something like this. And then on the right-hand side, for Faraday's law, we can plug this into here. So what the simplification will look like is as follows. Great. So now that we have this equation here, we can notice that our Gauss's law here just simplifies to 0. So that rids of that operator. And we can begin to see our wave equation formula. Just rewrite it as such. We can drop our negatives here to achieve this formula. Finally, one more simplification just with our permittivities and permeabilities here. Our speed of light inversely proportional to the square root of the permittivity and permeabilities. So finally, we can write our Laplacian of our electromagnetic, or our electric field. That's 1 over the square root of the speed of light times our second order derivative with respect to time for electromagnetic field. So this is now in the form of a wave equation, just with the spatial disturbance on the left results in our temporal disturbance on the right related to the speed of light. So this is just for the electric field, but by using the exact same process here, and taking Ampere's law, we form a very similar equation here. So these are our electromagnetic wave equations.
Okay, we will now move on to the plane wave. And here we're just going to conduct a couple of tests using Maxwell's equations to realize properties of the plane wave. So for test 1, we're just going to be using, just looking at Gauss's law, which in our case is just equal to 0, because we're still considering a simple medium. And taking this further, for both the electric and magnetic field, you can see that they're both equal to 0. Explicitly stated here. So what we can see or gain from this is that there is no field component along the z direction, which in this case is our direction of propagation. So we can conclude that the wave is transverse. So in other words, the oscillations from our electric and magnetic fields are orthogonal to the direction of propagation for our plane wave. For test 2, test 2 just looks at the relationship between our electric and magnetic field. So to do this, we're just going to be using Faraday's law. And from Faraday's law, we can generate these two expressions. Basically just for our electric field components, which are in the y and x direction, because we just confirmed that they're not along z. So those are just equal to omega so yeah, it's just equal to omega times our permeabilities multiplied by our magnetic fields components. So just from these two equations here, we can actually simplify this further into a more general case for the complex magnetic field, which would look like this. Z, our direction of propagation, just crossed with our electric field. So our spatial and temporal frequencies here, we know that these are equal to our refractive index over the speed of light, just where our refractive index is square root of our relative and free space permittivities. So just writing this out further here. I'm just going to keep simplifying this down. Such. Taking this one step farther. Get something that looks like this. So at this point, we're going to define these two expressions here as this is the free space impedance, and with our this one right here is our relative impedance. Oops. So finally, we can write this equation out as such. What can we draw from this? Well, our magnetic field can be seen to be orthogonal with our electric field. And from the first test, we know that both our electric and magnetic fields are also perpendicular to the direction of propagation. So this really summarizes some of the important properties of our plane wave. So today we've gone over just some of the fundamentals to a wave, how to express it in its sinusoidal and complex forms. Also, we've taken Maxwell's equations and shown how to make wave equations from the Maxwell equations. And then we've most recently just looked at some of the important properties of a plane wave. So finally, I'm just going to draw out or sketch a plane wave in its simple medium here, just for a final visual representation and sort of summary of what we've gone over. So this is just our electric field. field with its amplitude dependent on the electric field and scaled by our free space impedance and relative impedance. So we can define our wavelength here just as 2 pi over our spatial frequency, and also the period of the wave, or the time it takes to go full cycle up and down, just as 2 pi over our temporal frequency. Finally, we can define our wave propagation vector just to be our temporal frequency times our refractive index, the z direction, divided by the speed of light. So, finally, just want to state that there's nothing special about the z-axis being the direction of propagation. We just use that in this video tutorial just as an example, and I'll just leave you with the more general forms of our wave equations to be as such. The biggest difference being we now have a dot product to represent our spatial term there. Thank you very much for your time watching this video, and good luck on the final exams, everyone.